Okay. Okay, so, well, this being a conference on a very special phase, I thought I would like to ask the following question. Is the quantum phase the fundamental object in quantum mechanics? In other words, if we want to think of the most fundamental way of encoding quantum mechanics, is it encoded in the quantum phase? And, it's somewhat of a vague question, so there's, you can come up with a couple of answers. You can say, for instance, well, in some sense, yes. Feynman path integral, for instance, is formulated in terms of integration of, or a sum of phases, each phase assigned according to a specific trajectory. What I have in mind is a little bit more of what you see, for instance, when you do the semi-classical or WKB expansion of the Feynman path integral, and it's that if you look at the amplitude, all the information in the amplitude is basically contained in the phase. Once you know the phase, you can obtain the modulus of the phase. In other words, the transition probability itself, just based from the phase. And in the WKB case, it just comes out of some conservation laws or something, just consistency with current conservation. So to make my question more precise, I would just like to ask the following question: Does there exist an exact WKB type formula? So something of the form where you have some unitary operator sandwiched between the two states, and everything can be expressed in terms of the phase. So what I'm thinking of here is that there is some phase that depends on the unitary operator, and of course it's going to depend on these states, which are regarded as fixed, and then the modulus, which is going to be some function null, or something that can be obtained once you know how the phase behaves. Okay, and the answer to this question is yes, indeed you can do it. And what I've tried to show is two formulas where you can do it with different contexts. So in the first case, what I want to treat is an n-dimensional Hilbert space. And the unitary operator that I'm going to sandwich in there is going to be a unitary operator of SUN. It's going to be parametrized by basically I'm just going to look at all possible SUN operators. So I'm thinking of this object now as being a function of SUN, and the x mu are just going to be my SUN coordinates. In this case, SUN, is a compact Euclidean manifold. You can introduce a metric. The metric is actually, a natural metric there that's inherited from what's called the Killing form. And if you just use arbitrary coordinates, you can express the metric in this way. So it's basically a trace of derivatives of the unitary operator and its Hermitian conjugate. Okay. So if I now look at this object that I'm studying, let me look at the way the gradient of the phase behaves as a function of basically the group, as I move around in the group. Okay. And so this turns out to be this imaginary part of this matrix element, which is just the derivative of the unitary sandwiched divided by the unitary. If you know a little bit about weak values, this is essentially something similar to weak values. That's actually how I got interested in this whole problem. Okay. And so what we'd like to do is to compute the gradient of the phase using this metric. So in order to do that, what we do is, it becomes convenient to use what we call the Maurer-Cartan orthonormal frame. These are basically left invariant forms, and the idea is that we want to expand these things in, let's say, an orthogonal system, an orthonormal frame. So essentially, this is a vector in the Lie algebra of the group, and so what we're using is as a basis some Gell-Mann matrices. So they play the role of your orthonormal vectors, and then the theta a mu is essentially your Vielbein for this thing. The Gell-Mann matrices, of course, satisfy the conditions that we associate with them. They're traceless, and the inner product between two matrices is 0 unless they're the same. So in terms of that, you can express the metric and the inverse, which you need, of course, to calculate the gradient, the modulus of the gradient squared. You can express it in terms of these theta functions, which are basically the Vielbeins. Okay, and then it's a matter of using some identities. So we use this nice identity with the Gell-Mann matrices. If you add over all the matrices sandwiched around a certain operator, then you get this expression that's basically a combination of the unit operator and the operator itself divided by n. Okay, so now it's just a question of a little algebra. Going back to our definition of this phase gradient in terms of the imaginary part of these derivative of these gradients of u. Okay, and then you find these two things for this quantity squared. You find that it's 2 times 1 over n minus 1, and then if you take the modulus squared of the quantity, the inner product with itself, you get another formula, which interestingly then involves exactly the modulus squared of the amplitude that we were seeking, or that we were talking about. So, you can just play around with that and obtain a nice expression for the phase gradient, for the gradient of the phase squared. It turns out to be the inverse of the transition probability plus 1 minus 2 over n. And if you work it out correctly then, and then you just get some you can get this nice final formula that satisfies exactly the conditions that we wanted to obtain, which is basically this thing, the phase is there. Okay, and once you have the phase, you just construct the gradient squared of the phase, add this thing up, take the square root, and there you have your final formula. So what this is telling you is essentially, if I know the state psi, and then I do, let's say, infinitesimal variations of the state with through the action of SUN, but I look at all the infinitesimal variations, then I can and I study the phase as I do these things, then that information is going to be enough to reconstruct the whole transition amplitude. Okay, and just to see that it works, let's work out the SU2 case, which is simple. In the SU2 case, so you have this denominator here, n minus 2 over n. So n in the SU2 case is 2, so this goes away, and then the formula simplifies to just the inverse of the magnitude of grad S. SU2 is, of course, the same thing as the 3-sphere. So we use coordinates that are natural to the 3-sphere. Those coordinates actually arise when you parameterize your SU2 element as, in this sort of direction and angle type thing. Chi is playing the role of a rotation angle, and then we dot sigma with n, so a direction in space that's parameterized with the usual polar angle. So we have the 3 polar angles. If you work out the metric metric turns out to be, as expected, the metric of S3 of the 3-sphere, and so the gradient squared in that case is, it's just this formula where you just take basically the inverse of the coefficients that you find in the metric. Okay, so that's basically all we need. And then let's just look at a very simple example. So let me take, for instance, the matrix element with a spin up and a spin down of the unitary operator. That's very easy to calculate. It's just basically, when you expand the unitary out, you get this sum of sigmas, and it's only the sigma minus that is going to contribute, so you eventually end up with that. And the point there is that we only need to look at the phase because everything else is going to be developed from the phase, and that we can see the phase is just e to the I phi. So, so the phase angle is phi. The derivative of the phase angle is 1. Therefore, the gradient squared is cosecant squared of chi, cosecant squared of theta. And because of this formula that we have, you just basically invert that and you get the transition probability. Sine squared of chi, sine squared of theta, which is exactly what you would get from you know, what the result that we have. So there's a couple of interesting things that you can say about how, you know, the phase and the probabilities interplay. If my computer allows it. Wait. Okay. So from this formula, we can see two interesting things. One is we find, well, of course, the probability, the transition probability. We may find a u that makes the transition probability 0, and so that automatically tells us that the phase at that point has to diverge. So the phase diverges around the nodes, and this is, you know, sort of a typical behavior that's expected. The other thing that we find is something that's connected to superoscillations, and I won't have a lot of time to deal with that, but the point is the transition amplitude in modulus has to be less than 1, and that actually imposes a minimal condition on the size of the phase gradient. So the phase, in some sense, if you look at it on the whole group, it has to be oscillating. And that oscillation is actually like a super oscillatory behavior. Okay, so the second formula that I want to deal with is connected to the fact that in sandwiching this u, well, this SUN is really very redundant because, you know, you have a subgroup that just leaves the state, let's say your psi, it leaves it alone, and then you have this other little group that the only thing that it does in the state is just change the phase. So it's not really moving the state in the ray space. You know, and so you have like all these coordinates that are somewhat redundant. So what I want to do now is just look for a sort of a reduced formula where the argument now is the state psi. So we're thinking of basically only just possible you know, different states on the ray space. Of course, we have this problem, and is that we have an assignment of phase, which is essentially arbitrary. So the way we think about it is basically we have this base manifold. So we have a fiber bundle. We have a base manifold, which is the ray space, the space of rays, and then there's a fiber, which is the phase. And so when you talk about psi, you're really thinking of some section on this manifold. And we want to look for the same formula. Now, I'm going to do it a little bit fast because time is running short. But the point here is, what you find here then is it becomes a gauge problem, right? Because if you change the phase of psi, and this is a, you know, it's not a constant change. It can depend on where you are in the manifold. Okay, then of course, what do you see? Well, you see that the phase in this amplitude has to change by, you know, if I add this extra phase eta here, eta now appears in the phase again. But of course, the transition probability has to be invariant. So that's a gauge invariant object. So what we want to do is to look at gauge invariant versions of the gradient of the phase. Okay, and that we do by introducing this the Berry-Simon or the geometric phase connection. Okay, so which is given by this formula. So this is the connection that appears in the context of geometric phases. So once we do the gauge change, what happens is, well, the connection changes also as a connection. So you end up with that extra piece, and the extra piece is exactly the thing that you need to subtract from the gradient of the phase. So we can define something that we would call it, say, like a gauge invariant part of the gradient, which is just take the gradient of the phase and then subtract the connection. And if we do that, okay, and then, you know, a miracle happens, and that we won't be able to do it here. You end up with another formula, so it can be derived from the previous one, which involves the phase gradient. And now all these factors of n are gone, and so we have this thing. So it's basically the inverse of the phase gradient, of the gauge invariant part of the phase gradient squared. plus 1. And the metric now is the natural metric on the space of quantum states, which is this Fubini's 2D metric, which we can write like this. So very fast, I want to just discuss the example of a spin 1/2 in that case, because there's a couple of very interesting things that are connected precisely with the Aharonov-Bohm effect. Okay, so what we want to do now is, okay, let's parameterize, a spinner, okay, with the angle on the Bloch sphere, and let's use a specific parameterization like this one: cosine of theta 2, sine of theta 2, e to the I phi. That's like a choice of gauge in a sense. If you calculate the vector potential in this case, where the vector potential meaning the geometric phase connection, okay, the vector potential, we know this is the vector potential of essentially a monopole. If I look at the Bloch sphere embedded in 3 space, so it's going to be the vector potential of a magnetic monopole, and that's what I'm representing here. With a string, it's a Dirac monopole, and so the string is running along the negative z-axis. Okay, so we have these flux lines that are going like this, and they're going out like that. Okay, now let me look at something. So a transition amplitude where I have, some other direction. I just take the inner product between the two, and that's going to be, of course, the probability that we know is easy to compute, and then e to the I times the phase, and the phase is usually not very easy to compute. So I'm not going to write it. But if you do the computation and you actually compute the gradient, the gauge invariant part of the phase, you end up with an expression that's also the expression for the vector potential of a monopole. But in this case, the string is directed. So you see, what happens is, of course, when the amplitude is 0, you're going to get a singularity, and the singularity is going to be in the gauge invariant part of the phase. So the string is actually along the minus m direction, and the strength of the monopole comes with a minus sign. So you get the flux lines going like this. Okay. So finally, you say, okay, well, if we know that, then we can just add the vector potential, and then we get the phase gradient itself. So adding the phase gradient is like adding, well, the monopole vector potential that we had from the connection, plus the monopole vector potential that we had from the invariant part. And so you're adding two fluxes. They're, of course, adding with a different sign. So essentially what you do, so you get this total flux line, like this, which, of course, gives you so it's basically all the flux is trapped here. So over here we have, let's say, like 0 magnetic field in this sense. So this is basically the phase gradient here is behaving like a Aharonov-Bohm phase, and of course it should be with the flux and strength. Let's see, it's consistent with what we can expect of the phase, and it's that if I go around the fluxen like this, that's going to pick up a phase of 2 pi. And so generically, what we'll see is actually in a transition amplitude like this, if we look at the phase itself, the phase is generically going to have 2 singularities. One which actually comes from the vanishing of, this one, that comes from the vanishing of the amplitude at that direction. The other one is connected to the connection itself. Okay. Yes. Yes.
In 3-dimensional space.
Yes.
How does the formula look then?
Well,
one stage must be 1 dimension must be like WKB.
Yes.
We know what that's like.
So well, I've played a lot with that. I'm trying to get it. So n, of course, becomes infinity. So this factor here becomes a 1, and your SUN is now the group of basically, diffeomorphisms in phase space, in a sense, the quantum version of this. So it's complicated.
Well, it's very complicated.
But
I mean, you want to check your gradient has
yes.
to be carefully interpreted, doesn't it? Because instead of these x's that you have, which are the coordinates in the Hilbert
Yes.
space of the spins, you want to convert those into, as you say, the phase space.
Yes, absolutely. I've been playing around with it. I haven't been very successful. That's really where I'd like to get at some point. Yes. Thank you.
Okay, so let's proceed to our next speaker.